Welcome to this explainer. Today, we're going to crack the code on DGCA CPL radio navigation and turn some pretty complex STRI theory into serious exam success. I know this topic can feel really heavy, but stick with me. By the end of this session, you are absolutely going to own it.
Imagine this for a second. You're at the controls of an A320, flying straight through the soup at night. You're in thick clouds, visibility is practically zero, and you are completely reliant on unseen radio waves bouncing around the atmosphere to guide you safely to the runway. That's the reality of being an airline pilot, right? Understanding exactly how these radio navigation aids work isn't just about passing a DGCA exam. It's about building the fundamental skills that will keep you, your crew, and your passengers safe when you can't see a single thing out the window.
All right, here's our masterclass flight plan for today. We've got core concepts, essential formulas, DGCA exam traps, and a 60-second rapid revision. Let's dive right in.
Section 1. Concept explained.
Let's strip away all that textbook jargon and build your understanding from the ground up, starting with how these aids actually work in the real world. First up is the VOR, or VHF omnidirectional range. Operating in the VHF band between 108 and 117.95 MHz, the VOR is literally the workhorse of en route navigation. Think of a VOR ground station like a massive rotating lighthouse transmitting 360 distinct magnetic tracks, which we call radials, out into space. Now, what's really fascinating is how the VOR receiver in your cockpit figures out where you are. It doesn't just look at one single beam. Instead, the station transmits two signals, an omnidirectional reference signal and a rotating variable signal. Your receiver simply compares the phase difference between those two signals to pinpoint exactly which of the 360 radials you're currently flying on. Pretty smart, right? But remember, because it's VHF, it operates strictly on line of sight. If a mountain rolls in the way, or if you drop below the curve of the Earth, boom, you lose the signal.
Okay, next up is the NDB, or non-directional beacon, and its cockpit sidekick, the ADF, or Automatic Direction Finder. The NDB is a simpler, much older ground beacon operating in the low and medium frequency bands. Unlike VORs, NDB signals travel as surface waves. This means they actually hug the Earth's curvature, which makes them fantastic for over-the-horizon or oceanic navigation. But here's the catch. The signal itself has zero directional information. It just blasts out randomly in all directions. So it requires your aircraft's ADF system, which uses a clever combo of a directional loop antenna and an omnidirectional sense antenna, to resolve a 180-degree ambiguity and literally point a needle directly at the station.
Finally, let's talk about DME, or Distance Measuring Equipment. DME operates in the UHF band and is essentially a secondary radar system. It kind of acts like a high-speed game of Marco Polo. Your aircraft sends out an interrogation pulse, the ground station receives it, pauses for a strict, electronically locked 50 microsecond delay, and then replies. Your aircraft times that round trip, subtracts the 50 microsecond delay, and calculates your distance using the speed of light. But listen closely to this part. DME measures slant range. It measures the direct hypotenuse through space from your aircraft down to the station, meaning it's always going to read slightly higher than your actual horizontal ground distance.
Section 2. The numbers and formulas.
So the absolutely crucial point here is knowing how to apply the math behind these systems. Let's slow down and walk through the three big formulas the DGCA loves to test. Formula number 1, the VOR maximum line of sight range. The formula is range in nautical miles equals 1.23 times the sum of the square root of the transmitter height plus the square root of your receiver altitude. Let's do a quick worked example. Say you have a VOR on the ground at 1,600 feet and your aircraft is cruising at 9,000 feet. Step 1, find the square root of 1,600, which is 40. Step 2, square root of 9,000, which is about 94.87. Step 3, add them together to get 134.87. Step 4, multiply that by the constant 1.23, giving you a max range of about 165.9 nautical miles. Now, here is a massive mistake alert. Students constantly add 1,600 and 9,000 together first, and then square root the total. If you do that, you will fail the question. You must square root the heights independently. Okay, moving to formula number 2, ADF relative bearing math. The ADF needle only shows relative bearing, which is just how many degrees the station is clockwise from your nose. To find your actual magnetic bearing to the station, the formula is magnetic heading plus relative bearing equals magnetic bearing 2. A great memory aid for this is Midnight helps radio broadcast more beautifully. MH plus RB equals MB. So for example, if your aircraft heading is 120 degrees and your ADF needle is pointing straight out your right wing at a relative bearing of 270 degrees, adding 120 and 270 gives you 390. Since that's obviously greater than 360, just subtract 360. Your true magnetic track to fly directly to the station is 030 degrees.
Formula number 3 is the DME slant range correction. Remember, DME is the hypotenuse. To find your true ground range, we have to use Pythagoras. Ground range squared equals slant range squared minus altitude squared. And this brilliantly illustrates a major rule. You absolutely cannot mix feet and nautical miles. You have to convert your altitude to nautical miles first. Let's say you're cruising at 36,000 feet and your DME reads a 10 nautical mile slant range. First up, divide 36,000 feet by 6,000 to get 6 nautical miles of altitude. Now apply Pythagoras. 10 squared is 100, 6 squared is 36. 100 minus 36 is 64. The square root of 64 gives you exactly 8 nautical miles of true horizontal ground distance.
Section 3. Exam focus. Let's see how they test this.
Let's move on and see how all this builds into actual DGCA trick questions, so you can step into that exam hall with total confidence and zero surprises. Here's a classic trick question for you. An aircraft tracks directly over a DME station at flight level 300. What will the DME ground speed indicator read at the exact instant of passage? Now, this tests if you truly understand what slant range does when you are directly overhead this station. The answer? 0 knots. Why 0? Because the DME equipment calculates your ground speed by measuring the rate of change of your slant range over time. When you are exactly directly overhead the station, your slant range momentarily stops changing entirely before it reverses as you fly away. Because the rate of change is briefly 0, the ground speed calculation just plummets and reads 0 knots. Next question, when does coastal refraction cause the greatest angular error for NDB signals? Well, since LF and MF radio waves travel faster over highly conductive seawater than they do over land, they literally bend toward the coast when they cross it. But the exam wants to know exactly when this bending is at its absolute worst. The answer here is when the signal crosses the coastline at an acute, shallow angle, typically somewhere between 10 and 30 degrees. If the radio wave hits the coast at a perfect 90-degree right angle, there's 0 refraction and 0 error. To mitigate this, pilots should just fly higher, or only rely on NDBs that are situated right on the coastline itself. Question 3. Why might your ADF needle suddenly swing violently away from the tuned NDB and point directly toward a dark cumulonimbus cloud? NDB signals are super vulnerable to environmental noise, and the DGCA frequently tests your knowledge of what we call the thunderstorm effect. It's lightning. The answer is lightning. Lightning strikes emit a massive, powerful burst of electromagnetic radiation right across the LF and MF frequency bands. The ADF receiver in your aircraft simply cannot distinguish between a legitimate 200-watt NDB signal and a billion-watt lightning strike. So it temporarily breaks lock from the station and literally points the needle right at the active storm cell. Section 4. Quick recall. Let's lock this in. Time for a 60-second rapid-fire revision of the absolute most testable facts from this entire lesson. Imagine you are walking into the exam hall literally right now. Lock these into your short-term memory. VOR operates in VHF, meaning it's strictly line of sight, and uses the 1.23 constant for range calculations. NDB operates in LF/MF, using surface waves, making it highly prone to night effect and thunderstorms. For ADF math, magnetic heading plus relative bearing always equals magnetic bearing. DME operates in the UHF band, uses a precise 50 microsecond transponder delay. And remember, slant range error is always at its worst when you are at a high altitude and very close to the station. Boom! Prerequisites completed. You now have the exact technical foundation you need to tackle your instrument approaches. And by that I mean ILS localizers, VOR arcs, NDB overlays, and your modern RNAV training. Everything builds directly on the concepts we just covered today. But listen, don't just take my word for it. The only way to truly own this material is to test yourself. Head over to CloudDeck.in right now, run through their practice questions on radio navigation, and make absolutely sure you are bulletproof for the exam. Because in the end, when you're up there in the clouds and the displays go dark, are you going to trust luck or are you going to trust your instruments? Thanks for joining me on this explainer, and I will see you in the next one.